The next important concept that we want to deal with is the concept of frame difference or objectivity. Now, assume that we have two reference systems. One is an observer who is fixed in this system O, and there's another observer fixed in this system O plus. Now, imagine that both these observers watch two events taking place at x1 t1 at the position x1 and time t1 with respect to observer O, and this blue event takes place at location x2 at time t2 for observer O plus. Similarly, the red event takes place at time x1 x2 t2 for observer O and x2 plus t2 plus for observer O plus. Now, what we obviously know is that both these observers will see different position vectors for this blue and the red events. So this guy will see x1 and x2, this will see x1 plus x2 plus, but they will both see the same separation between the events. So both of them will see the separation to be equal to x2 minus x1. Magnitude of x2 minus x1 will be this distance s, and x2 plus minus x1 plus will also be the same. Now this basic fact is the starting point of our discussion on frame indifference. Let us now assume that O is a fixed reference coordinate system. The coordinate system fixed to observer O is a fixed one, and its base vectors are denoted by EI with subscripts I, J, K, and so on. Whereas O plus is a rotating and translating coordinate system with respect to O, and its base vectors will denote them by E with subscripts A, B, C, and with a plus on the top. So EA plus and EI, these two sets of base vectors, can obviously be related through the instantaneous rotation tensor connecting these two coordinate systems. Let that instantaneous rotation tensor be Q of t, and its components are, let's say, Q, A, J, which are, as we know, defined as EA plus dot EJ. So this is the definition of the components of the transformation tensor for rotations, and this is the new coordinate system, base vectors of the new coordinate system dotted with base vectors of the old coordinate system. Now from this we can get a relationship directly between EA plus and EA. So for example, this relation, if you want EA dot, let's say, EK, then you would dot this relation with EK on both sides. So EA plus dot EK is QAJ delta JK equal to QAK, which proves this basic relation. And similarly, we can prove the relation from the other way around, follows from the same definition here. We can also prove that EIs are related as QAI EA. Now since EA plus is rotating and translating with respect to O, we can write the time rate of change of EA plus. So we can write it as time rate of change of EA plus with a dot is equal to QAJ dot EJ plus QAJ EJ dot. But remember, this is a fixed coordinate system, so EJ dot is 0, so you are left with QAJ EJ, and now you can replace this EJ through this relation, and you can write it as QAJ dot times Q, let's say, BJ EB plus, and this particular tensor, we will give it a name. We'll call it the spin tensor, and we'll give it a name. We'll call it omega AB. So omega AB is q dot aj. This is the rate of change of the rotation matrix itself times q bj, which can also be written as omega is equal to q dot q transpose. So this is how omega can be written, either of this or this. So this omega will play important role in what we are going to discuss. So this is called the spin. Okay. Now let us look at the position vector of a point. So here's the point, and the position vector with respect to the fixed observer O is x. With respect to the rotating and translating observer O plus, it's x plus. And now we first write the vectorial relationship between the two position vectors. Now note that C is taken from O plus to O. So in general, you should have x is equal to x plus c, but since we have taken c this way, it would be minus c, and therefore x plus is equal to x plus c. This is the vectorial relation between the vector x plus, position vector x plus, and the position vector x. Now we can write this vectorial notation, vectorial relation in different coordinate systems. For example, we can write it from the point of view of O plus, and then O plus will see this vectorial relation and write the components in his own coordinate system. So he'll write x a plus ea plus is equal to x plus c a plus ea plus. I'm deliberately leaving this x out because this equation obviously has to be written in one coordinate system, so you'll have to write the components of x in its own coordinate system. But before writing them down, let's note that in O's coordinate system, x is a vector which is given by xi ei, and then xi ei is q a k q a I e a plus. Therefore q a I xi are the components of this vector x in the O plus coordinate system. So we should write this as xa plus ea plus q ai xi ea plus ca plus ea plus. And then the component form of this would be xa plus is equal to q ai xi plus ca plus. The thing to note here is that these are the components of the vector x in the O plus coordinate system as observed by the observer O plus, where xi are the components for the same vector x for the O observer. Now we sometimes and in many books write this equation in this form. We will generally refrain from doing that because this might lead to a few confusions, as we will see later. What we have just shown is this vector statement is absolutely equivalent to this statement in terms of components. So the components are in the O plus system, and component wise, this is the equation that relates the components in the O system of x to the components in the x plus system. So this statement and this vector equation are absolutely equivalent. Now let us look at the separation between the 2 points as we saw in this slide. So here we made the point that both these observers will measure the separation distance similarly, equivalently. So one would measure it as x2 minus x1 mod of that, and the time difference is t2 minus t1, and the other would measure it as x2 plus minus x1 plus mod, and the time difference would be t2 plus minus t1 plus. These time differences have to be the same, so t2 minus t1 has to be equal to t2 plus minus t1 plus. So this has to be satisfied, and the distance between the two events will also have to be the same. Now this time difference is easily seen to be true if the times in O and O plus are related by a constant. So time t plus is simply t plus a constant, let's say alpha. Then the differences in time would always be constant. So this equation would be satisfied if t plus, the time in O plus, has this kind of a relationship with the time in O. So that's one point. The separation, now the separation, let's call it the vector S, is the difference between x2 plus minus x2 plus and x1 plus, or the difference between x2 and x1. Now the vector separation in terms of components in O plus would be, let's say, SA EA plus. In O it would be SI EI. Now SI EI can be written as SI Q A, let's say Q A I EA plus, which means that SA plus, this should be plus, SA plus will be equal to QAI SI. So the components of separation in the O plus system will be related to the components in the O system in this way. Now this is the definition of frame indifferent vector. So S is a frame indifferent vector because if we know its components in one coordinate system, we can find the components in any other coordinate system with the knowledge of just the instantaneous rotation tensor between the two coordinate systems. That's why it's called a frame indifferent system. So the observer in the O plus system would measure these components, observer in the O system will measure these components, then they will know how to relate these components together because they know the Q at that instant where they measured the components. Now therefore this is what frame indifference means. For a scalar is always frame indifferent because if you have a scalar phi and you measure it at x and t, if you measure this scalar at a corresponding time phi plus x plus plus t plus, these two have to be equal, where x plus, remember, is q times x plus c. So this is how the components of x plus and x are related. If this is the situation, then scalar measured by the two observers will always be the same. A vector is frame indifferent when their components are related by this relation. So a VA plus is given as QAIVI. That's when we call the vector a frame indifferent vector. Now a tensor A, let's say it connects, it takes a frame indifferent vector x and gives a frame indifferent vector y. Then in the O plus system, we would expect it to give a frame indifferent vector y plus. So A plus multiplied with x plus should give a frame indifferent vector y plus. Now this being a frame indifferent vector, y plus would be q times y, a plus into q times x, and therefore y is equal to q a plus, q transpose a plus q into x. So this must be equal to a. So a must be equal to q transpose a plus q, which means a plus should be related to a as q a q transpose, which in indicial notation can be written as a plus ab, let's say, is equal to q a I a I j. These are components in the O system, and then q b q times bj. So q ai q bj a ij is equal to a ab plus is the relation between the components of a tensor which is frame indifferent. So if the components of a tensor transform in this way, we can find the components a ab plus in terms of the components aij by a knowledge only of the instantaneous rotation tensor. Now, uh, now the idea is this, that if the components of a vector are related as VA plus equal to QAI VI, then the observers O and O plus see the same vector. They would write the same vector V as VA plus EA plus or VI EI. They would write the vector in this manner, and they would be seeing the same vector if the components are related through this relation. They are seeing the same vector. Similarly, they would be seeing the same second order tensor if they write this as AAB EA plus EB plus. They would write it like this. So O plus would write its tensor in this form. O will write its tensor as this, but they would see the same tensor if AB, sorry, this is plus. So if AB plus is related to QAI, QBJ, AIJ, if this is the relation between the components AB plus and AIJ, then both of them are talking about the same second order tensor, which means that V equal to V plus, this vector equation is absolutely equivalent to the statement VA plus is equal to QAI VI. The statement A equal to A plus, where A and A plus are second order tensors, is absolutely equivalent to AAB plus being equal to QAI QBJ AIJ. So these are component wise absolutely equivalent statements to these vector statements. Now let us look at the velocity of this point as seen by O and O plus. So O plus would measure V as VA plus EA plus, and O will measure it as VI EI. And now the question is, if they connect these two components through QAI VI equal to VA plus, will one be able to get the velocity components from the measurements of the other? Now, for velocity, we can do it in two ways. One, we can directly start with the equation between the position vectors. We know that for the position vector xa plus, the position vector seen by O plus, is equal to xa q ai xi plus ca plus. And now we can take derivatives of this. Xa plus dot is qai dot xi plus c plus dot, and then we have omega is equal to q dot q transpose, which means that q dot is omega q. So q dot here can be written as omega ab q bi xi plus ca plus. So I missed a term here. It should be qai xi dot plus ca plus. So you have qai xi dot, and qai xi dot is equal to qai vi. So and this is va plus. So we have va plus is equal to qai vi plus ca plus dot here plus so these two terms tell us that the velocity components cannot be obtained from the measurements of O by O plus by simply using this part. If that was the case, which means that if this was a stationary coordinate system and it was not rotating with respect to O, then of course velocity would be a frame indifferent vector in the two coordinate systems. But in the general case, when when O plus is translating and rotating with respect to O, velocity is not a frame indifferent vector. Remember, this is the spin, and this kind of gives you the rate at which O plus is rotating with respect to. Okay, so we can do it. This is one way of doing it. The other way could be let me erase everything here. The other way could be to start from the vector relations. So in the vector relations, we know that x plus, this is how we have written it, is q times x plus c. We take the velocity v plus derivatives with respect to time, q dot x plus q x dot, that is qv plus c dot, and then qx dot is written as omega q x plus q v plus c dot, and you can replace you can write this as qv plus omega times qx can be written as x plus minus c plus c dot. So what it tells you is the velocity seen by O plus is the transformed velocity seen by O plus a term dependent on the spin and a term dependent on the velocity of O plus with respect to O. So this statement and this statement are exactly equivalent, but we would prefer to do the calculations in terms of components rather than through this. We can look at the acceleration. I will leave most of the calculations to you. So we can start with the velocity. So we can start with v plus. We can start with v plus equal to q v plus c dot plus omega x plus minus c. Take derivatives on both sides. So this is what we get, and now we can do some manipulations. So we can replace this q dot as usual by omega q times v this remains as QA plus C double dot plus the rest of the terms remain. And now this quantity can be written as, from the velocity qv is omega times v plus minus c dot minus omega x plus minus c. So this term, this qv can be replaced by this, and if you do that, this is what you will end up getting. This is what you will end up getting, and from here we can discern many terms. For example, this is the Coriolis acceleration. So this is the omega times the relative velocity of the particle with respect to its own coordinate system, own coordinate origin. This is the centrifugal term, and this is the rate at which the second coordinate system, that is O plus, is accelerating with respect to O, and so on. So clearly we see that A plus is not equal to QA, and therefore we cannot call a frame indifferent quantity. Now what about the deformation gradient tensor F? So remember, F takes a vector in the reference configuration and gives you a vector in the deformed configuration. Now there are two coordinate systems, the plus coordinate system and the unplussed coordinate system, unplussed fixed coordinate system. So in the two coordinate systems, in the plus coordinate system, the components of this are xi, and in the unplussed coordinate system, the components of this are qai dxi. These are the components in the plus coordinate system, and therefore the two observers, the first observer will see dx plus equal to f plus d capital X. Both of them start with d capital X. The d capital X is common to both the observers. So they are trying to see what is the f that gives them the d small x that they see. O plus sees d small x plus. So he infers that his deformation gradient is f plus. The fixed guy O sees dx, and his deformation gradient is just f. So now because dx plus is q dx, dx plus is q dx, that is equal to f plus d capital X, it must mean that that d small x is equal to q transpose f plus d capital X, which means f is q transpose f plus, which implies that f plus is q times f. So this is how the deformation gradient transforms when looked at from a rotating and translating coordinate system. Now once we know this for f, remember for second order tensors, the transformation rule is q transpose equal to a plus. But that is not true in case of f plus, because as I've discussed earlier, f is a two-point tensor and its transformation rule is different from regular second order tensor transformation. So you must remember this distinction. Now once we have got the transformation rule for f, then we can see the transformation rule for C is f transpose f, which is equal to so C plus would be f plus transpose f plus, which is f transpose q Q f. Q is proper orthogonal, which is equal to f transpose f. So C plus is equal to C. Similarly, E is half of C minus I. So E plus will also be equal to E. Now for the rates we have to be a little bit careful. For example, let's try to find L. Uh, let's try to find how L transforms. So L we know we know this relation F dot is equal to LF. So in for the O plus observer, F plus dot should be equal to L plus F plus. Now F plus dot is, because F plus is QF, is Q dot F plus QF dot, and then this is Q dot is, remember, omega times Q F plus Q F dot is LF. Again, we can replace this by omega QF is F plus, QLF can be written as QL Q transpose F plus, which means that F dot plus F plus inverse, which is equal to our L plus, is equal to omega plus QL Q transpose. We better write this in initial notation. So L plus AB will be equal to omega AB plus Q A I Q B J L I J. Now, if you want to write the vector equivalent of this equation, this is actually not. This is where the confusion lies. This looks like a vector equation, but you have to critically assess the components from the tensor itself. Now, if you look at this component equation, what this tells you is that LAB plus are the components of L that the O plus observer sees, and they are related to the components of to the component seen by observer O by this relation. Now, if I want to write this equation in the EA plus coordinate system, I would write it like this. Completely in the EA plus coordinate system, I would write it as LAB, where LAB are the components of LIJ in the AB coordinate system. Remember, I have to write the tensor equation in one coordinate system only. So this whole thing is actually the component of Lij, components equivalent to Lij in the AB coordinate system. So this is actually the same tensor L. If I write L as LAB EA plus EB plus or Lij EI EJ, I get the same tensor, and the components are connected through these two equations. So if I now want to convert this into the true vector form, this would be L plus equal to spin plus L. This would be the right way of writing the vector equation, which would translate immediately to the component equation this, which in turn would translate to the component equation this, with this LAB replaced by this. LAB are components of L in the AB coordinate system, which are given by this. Now you can still choose to write L plus in this manner, but then you must realize that these are actually the components of L in the XYZ coordinate system to the X plus Y plus Z plus coordinate system. So this leads to a bit of confusion. This is the right equation that connects L plus and L, as long as you remember this fact that this quantity is equal to this quantity. Now, once you have got this, it is easy to see that because this is skew symmetric, D plus is equal to D, because that's the symmetric part of L, and W plus, remember, is half L minus L transpose. So W plus will be let's erase this. So once we have figured out that L plus is equal to L plus omega, W plus is half L plus minus L plus transpose, which will give me half L plus omega minus L transpose minus omega transpose, and omega and omega transpose are negatives of each other, so this will be because minus omega transpose is equal to omega. So this is what you get. So W plus will be equal to W plus omega, or omega is equal to W plus minus W. So D is frame indifferent because it transforms this way. L is not frame indifferent, and W is not frame indifferent, it transforms in this manner. What about stresses? We know that the Cauchy stress connects the normal at a point on the deformed surface to the traction at the point on the deformed surface. So, so in the O plus system, we would expect this to translate as T plus sigma plus N plus, and we can show that the normal vectors are frame indifferent. T is not strictly speaking a vector in the sense that it doesn't belong to a vector space, but T and T plus are connected as T plus equal to QT, and using that we can easily show from starting from here that sigma plus has to be frame indifferent second order tensor. We can now look at, once we know this, we can look at the nominal stress, which is, we know, related to J F inverse sigma, and then in the O plus system the nominal stress should be related to J plus F inverse plus F inverse plus sigma plus. In place of sigma plus, put this. So use this in place of sigma plus, and then you get this relation between the nominal stress in the O and O plus coordinate system. For the nominal stress, you see that it's like the deformation gradient. So if you write the first peak as stress, which is the transpose of the nominal stress, then you will write this as QP. P plus is equal to QP, which is exactly the same as F. This is also a two-point tensor, and that's why two-point tensors for frame indifference have to transform in this manner, whereas tensors, second-order tensors like the Cauchy stress, transform in this fashion.